Hi, my name is Ankur Chaudhary, and today I'll be discussing my research work, Autonomous Security Analysis and Penetration Testing. These are my co-authors. This is my Twitter handle and email address. So the IoT devices are continuing to grow, and this slide gives a perspective that the estimated market of IoT devices will be 25 billion, and the predictive cybersecurity expenditure by 2021 will be $1 trillion. The penetration testing market will also grow to 3.2 billion in year 2023. We have a shortage of cybersecurity workforce by 3.5 million currently. So imagine what it would look like in year 2023 or 2025. And many organizations are reporting that they have lack of either cybersecurity staff, or the current staff is not trained enough to perform the duties of cyber security operation center within the context of their organization. So all these things point to the need of automation in cybersecurity. And that is why we want to discuss some of the AI technologies that are being used in automating the penetration testing framework. So first is PDDL, which is used for encoding the domain knowledge in form of the predicates and actions. So basically, we are creating a rule set in penetration testing. And based on those rule sets, we obtain the equation, obtain the optimal policy. Then we have Markov decision process, which is encoding of the state actions and rewards. And in terms of penetration testing, we encode the information about different vulnerabilities in the network states, which we obtain by exploiting these vulnerabilities and the rewards, and how some of these rewards are formulated in terms of penetration testing environment. In certain situations, the actions that are to be performed, there is uncertainty over the action. So the partially observable Markov decision process is used in existing research to model this uncertainty over the actions. But there are some issues with the current way the automation of penetration testing is performed. With PDDL, your plan is as good as the rule set that you are using to encode this AI framework. And with POMDB, basically, you have this scalability issue. As the number of state grows, it becomes very hard to find the optimal attack plan. So we consider this motivating example. Consider an attacker located on internet, and he's trying to compromise the database server. So with the goal of compromising database server, he would first try to access the public web server. Or what he will do is create a fake website and wait for the workstation to download some malware, which he will use to pivot from the workstation to the database server. So after he has obtained the access to these internal resources, either web server or the workstation, basically he will try to see that he pivots to the database server. So he identifies a SQL injection on the database server and basically connects either through workstation or the web server. And basically he establishes a connection back to his command and control center to maintain persistence. So we observe that attack is multi-stage. The attacker can have multiple attack vectors to target these vulnerabilities. He can go through multiple hosts. And from a penetration testing perspective, like if the objective of the penetration test is to compromise some critical resources in the system, then the penetration tester can perform this attack kill chain to compromise the intermediate resources, leading up to the higher reward resources. So we use attack graph as a way to model these multi-stage, multi-hop attack scenarios. The nodes represent the exploits and the vulnerabilities, like execute code can be one node in the attack graph. And the edges basically represent how you exploit these vulnerabilities. So for example, if you have a user privilege currently in the system and you have a network access, so those will lead to execution of code on the web server if it has a vulnerability, and then you can have an edge that transition you from a user to a root node. So the condition that need to be satisfied for the vulnerability to be exploited are known as precondition, and the privilege that you obtain on exploiting certain vulnerabilities is known as the post condition in attack graph. So basically in attack graph, you insert the information about the host configuration, the network configuration, the principal which tell you like the current configuration of the different system, the interaction rule which tell you like what kind of access has been configured, and the current security policies, and the reasoning engine. In our case, we use Malwell, but there can be other attack graph framework basically use this information to tell you like what are the different ways in which different security vulnerabilities can be exploited in the system, and how attacker can reach to different privileged nodes in a network by compromising these different vulnerabilities. So if you consider the attack graph of this system, the oval nodes represent some information, for example, the existence of vulnerability or the network access. And the oval nodes basically represent the privilege obtained by exploiting these vulnerabilities. So you can consider like one as the root where we want to reach, and 0 as the initial user state on web server in the system. So from the web server, if you have say user privilege, and basically you are able to obtain network access and there is a vulnerability, then you transition to root on web server, then you use that vulnerability to try and exploit the SQL injection on the database server and eventually reach your goal node. So how does AI factor into all of this? So our aim with the use of AI is to create a sort of system which can be used by penetration testers to keep on coming up with automated attack plans. So if you are going to your house on a busy day and you have a mental map of which street you are supposed to take, but there is a traffic jam in between, then you are stuck. But if you were using a GPS that has analyzed the situation of the traffic, then you will be able to reach the home faster. And in similar way, if you consider penetration testing, currently the pen testers have a knowledge map of the system based on what they have done in the past. But if there is an automated system that analyzes what are the different network configuration, the different privilege levels, then you can use this information to basically come up with automated attack plan. And in effect, it works as automated GPS, which lets you navigate through the landscape of these security vulnerabilities. So if we revisit attack graph and we consider FTP server that we are planning to compromise as a penetration tester, there are different ways you can approach it. Like you can go from SSH to FTP directly, or you can first try to compromise web server and go to FTP. And on the left, you will have the attack graph that gets generated. So basically with access to SSH, you exploit SSH first, get root on SSH, and then exploit FTP, or you start by exploiting SSH, then you exploit the web server, and then you exploit the FTP server. So with reinforcement learning, what we are trying to do is train our AI algorithm to interact with the environment repeatedly and learn an action plan. So with different states, the agent arrives at the goal node by interacting with the environment and learning policy, which is a set of best actions to take in a given situation. And Q-learning is the method that is popularly used to learn policy. Basically, you have state, and in state you perform an action, then you receive reward. So the reward of being in current state, and the possible future rewards that determines your optimal policy. And gamma means how much importance you place on the future rewards, like if being in current state is more beneficial compared to the future rewards, that is determined by this value gamma. And alpha is learning rate, like how fast your algorithm can learn. But there is a problem with this Q-learning approach. Like if you have environment with, say, 10,000 states and there are multiple actions per state, then you'll need a lot of memory to represent this state space information. And it is a very slow and time consuming process to explore these states and create a table which basically you use to come up with the optimal policy. So it is better to use machine learning to approximate the Q values. So in the deep Q network, which we use in this work, we use a neural network to approximate Q value function, and the experience that we have of interacting with environment, we use that to come up with the heuristic, or like the heuristic Q value. And we use a loss function to derive the policy. So we calculate the mean squared error of the current Q value and the optimal Q value. And in this way, we use the deep Q network to find out the optimal policy. So in terms of states, action, and rewards, basically the state represents the privilege level in our attack graph. So basically S0 can be user, S1 can be root. The reward, we use the CVSS score of different vulnerabilities to come up with the reward. And the transition probability between different state is dependent on how complex it is to exploit a vulnerability. So if it's a low complexity vulnerability, we have probability value of 0.9, like it's very easy to exploit and reach to S1. If it's a high probability, high complexity vulnerability, we assign value 0.2. So if we revisit the example that we had, basically, we can convert the nodes in the attack graph to state representation. Basically, in state S0, the attacker is still on internet, and in state S1, he reaches the FTP, and this happens by exploiting a particular vulnerability mentioned here. So basically, we represent the states actions from the information present in the attack graph. We use the access complexity to assign probability values. And then we use the reward values from the CVSS score of these different vulnerabilities. So basically, if you take no action in state S0, you receive a low reward. But if you exploit a particular vulnerability, you receive a reward of 6.4, which is high reward. And your eventual goal is to reach S2. So we represent this reward matrix. And to put everything in perspective, we encode states, which is user privilege level, action, which are actions you can take to exploit the vulnerability. The reward is CVSS value. And the transition probability is based on the access complexity. So here you can come up with two policies, like one can be to exploit SSH and then exploit FTP, which gives reward total policy value, or the value when the algorithm converges is 15. And policy P2 gives a higher reward. So basically, this is a optimal policy in this case. So to put everything in perspective, we parse the attack graph. We find the CVIDs of this different vulnerability. We obtain the access complexity of each vulnerability and the CVSS score of vulnerability. We create the reward matrix, which is based on CVSS score, the transition matrix, which is based on the transition probability, and use all this information to encode in form of a Markov decision process, which then our deep Q network uses to come up with the optimal policy. So this is one example, like the penetration tester was supposed to exploit certain vulnerabilities in the network, and this is our encoding in the OpenAI GIM format. So from this example, we learned that the intuition of manual penetration tester would be to first try and exploit these networks which have a lot of services. But this may not always be the best approach. We found out that optimal policy will be to first exploit the SMTP server as opposed to directly going for the subnetworks with high vulnerabilities. And we observed that small batch size, basically we batch the states in batch sizes. They provide optimal reward value, and we can see that they have better running time as well. So for the convergence of algorithm, it is important to have smaller batch size in our DeepQ network. And we analyzed the framework on a network of 300 hosts. It took us 70 seconds to come up with optimal policy. And even in the worst case, basically, the running time was only up to 400 seconds, which is a significant improvement in terms of scalability compared to manual penetration test. So basically, ASAP framework is able to find out the hidden attack paths, which are often missed in manual penetration test. It generalizes well to different networks, and it scales well on a large network as well. And with that, I am open to any questions. And thank you.